Okay, section 5 here of exam 2. We're going to talk about different types of limits. Same basic concept, but as you can see, this is not x approaching a value a, it's actually x approaching infinity or x getting larger. So it's the same basic idea, right? What happens to this particular function as you plug in larger values of x? Again, we can set up a chart for this, but we're not going to. We're going to, jump sort of to the exact way to evaluate this. Um, but you can obviously, what happens if x is 100, 1,000, 10,000, is this thing getting closer or anything? And it turns out that if you begin to plug in some values of x, you will find that it gets closer and closer to 1. In fact, we can make it as close to 1 as we want, right? So this should look familiar. The definition, right, we say, or we write this and we say the limit of f of x as x approaches infinity is L. In other words, we can make f of x and L, right, as close as we want by choosing values of x that are sufficiently large. So again, right, this as close as, this is not the precise definition. Is there a precise definition for this particular type of limit? Yes, there is. Are we going to cover it? No. It's not that much different, but obviously you can see there's no delta, right? There's no distance on the x-axis. X has to get larger and larger. So it would require a slight little tweak, but we're not going to cover that. It's a little bit outside the scope of this class, but there is one. Know that there does exist a precise definition for these types of limits as well. Same deal here, right? The limit as x approaches negative infinity. In other words, we can make f of x as close to L as we want by picking values that are large and negative, not small, large and negative. Okay, negative infinity is a large number. So now we can talk about the idea of horizontal asymptotes, which I'm sure you're familiar with in terms of limits. So as you go to the right, as x gets larger and larger, if the function approaches or gets closer to some L, or if you go to the left and it gets closer to some L, then we say L is a horizontal asymptote. Okay, that's left end behavior, right? You may have heard it referred to as end behavior. What happens in this particular case? So clearly as x gets very large, 1 divided by a very large number is a very small number. So this limit does exist and is indeed 0, okay? That kind of gives us this theorem, which is not that big of a deal. Just be aware of it because that's kind of what we use for the method. So basically, 1 over x to the r, whether you go to infinity or minus infinity, goes to 0, which should be intuitively obvious, right? Dividing by larger numbers is going to give you a smaller number. What we do is we use this fact here to evaluate limits as x approaches infinity or minus infinity. So I'm going to show you this one kind of in gory detail here, step by step, and then we'll get to what you really need. So here's a limit as x goes to infinity. This is a standard rational function, 3x squared minus x minus 2 on top, and the 5x squared, etc. on the bottom. So how do we evaluate this? What is the technique? Well, essentially we take the highest power of x in the bottom, right? That's why this is in capital letters, in the bottom, in the denominator. And we divide every term by it. So I have 1, 2, 3 terms upstairs, 1, 2, 3 terms downstairs. So every term, which is this step here, I'm dividing by x squared. That's the highest power in the bottom. Once you cancel everything and simplify, you're left with this. Now, what happens to this term, this term, this term, and this term as x gets very large? Well, they all go to 0 from that previous theorem. So the only thing that's left is, of course, the 3/5, which we have right here, right? That's where that comes from. So, that obviously begs the question, well, can't you just look at it and see the ratio of coefficients with the x squared? Well, sure, but I do need to see some work. So do you have to put this step in? No, at least put this one in. So it shows me at least that you know the technique. Maybe next semester when we get stuff like this, I can say at that point in time, okay, you've done enough. You guys know what's going on. You can just go right to 3/5, okay? Also, and we'll get to it in a second here. Obviously, if the degree on top, right, if the degree of the top is greater than the bottom, what's going to happen? Well, it's going to keep getting larger, right? And if the degree of the bottom is greater than the top, it's going to keep getting smaller, right? So it's either 0, infinity, or some value ratio coefficients, which I'm sure you could figure out, but this is what we're looking for work. So again, if we want to talk about vertical and horizontal asymptotes of this rational function, which you have done in the past, probably just not in terms of limits, To find the horizontal ones, you would find two limits, right? What's the limit as x approaches infinity of y? What's the limit as x approaches negative infinity of y, right? Again, you would divide the highest power in the bottom as x squared. But we can see that the top is larger, so there's not going to be a value there. It's going to keep going up. But you should do this. You should try this on your own. Okay. How do you find the vertical? Well, when is the denominator 0, right? When is x squared plus 3x minus 10 0? Well, clearly that factors, right, into 2 and 5, and it looks like it's a plus 5 minus 2. Does that work? Plus 5x minus 10. Yeah, so it looks like you'd have to investigate also the limit as x approaches negative 5 and the limit as x approaches 2 and see what happens there, right? If any of those answers from the left, right, or either, left, right here and from the left, right there, if any of those four go to plus or minus infinity, then we have a vertical asymptote. What happens to e to the x as x gets larger? Well, e to a larger and larger value obviously continues to go up. So this is infinity. Or, right, does not exist is fine. This is probably a better answer because it's a description of how it doesn't exist, but both are okay. How about this one as we go to negative infinity? Well, as you go to the left, right, what does e to the x look like? Right, you should know what e to the x looks like. Right? And so as you go to the left, it's actually asymptotic to the axis. So it gets very small. In fact, it's equal to 0. How about this situation here? What happens to this graph as we head over to the right? Well, again, it just keeps doing, right? Just keeps oscillating. So does it actually approach a single value? Even though it's bounded above and below by 1 and minus 1, respectively, does it actually approach a value? It doesn't. So this limit does not exist. Okay? Does not exist. It needs to approach a single value. Here again, you can try this on your own. You can probably see what's going to happen, right? The degree of the top is greater than the bottom. If you wanted to divide everything by the, again, highest power in the bottom, so you divide everything by x. If you wanted to do every single step, it'd be x squared over x plus x over x minus 5 over x. 15 over x minus x over x. And then cleaning all of that up and simplifying, x is going to infinity. And we have an x upstairs plus 1 minus 0, right? Because that goes to 0. And then on the bottom we have a 0 minus 1. And plugging in large values of x, we're going to get a large positive divided by negative 1. So this is actually a large negative. Okay, you got to be careful with that. That minus 1 makes a difference. If it's plus 1, it would be plus infinity. So here's the worksheet. This is a little bit different, this question. I'm giving you the conditions and asking you to sketch a graph. So the graphs that you guys create may look slightly different, but they should have those properties. And then these are just two straightforward limits. And here again, right, already I'm calling up what we talked about earlier, like you should know what that graph looks like. This will be a helpful thing to know here. And then in terms of the homework, again, a couple different graphs satisfying these conditions, and these are just straight up finding limits, okay, which is what we really should be practicing a lot. It's very important that you know how to do these. So none of these are going to be charts or approximations. I want you to do these exactly using that technique. And then same thing here, right? Just similar to that problem in the notes. Okay, that takes care of this section 5.